Okay, let's go ahead and get started. So I have posted your homework 13 on active chemistry that goes into calculating some of the different colligative properties. So make sure you take a look at that. You already did it. Excellent. We do have a quiz on Monday that's going to cover chapter 11. So that's the mixtures, the everything from calculating concentration and the changes in colligative properties to understanding interparticle forces, being able to identify if I have salt dissolved in water, what are those intermolecular forces, and is that stronger or weaker than the forces between, say, hexane and pentane. So that's what we have coming up on Monday. Any questions? Okay, I asked for this a minute ago, but several people walked in since then. If you have your test corrections, go ahead and bring those to me. If you just got back your test today, then you can turn those in next week. Finish on Wednesday. And we had calculated the molarity, or not the molarity, the change in the boiling point as being 0.12. Since this was acetone or acetic acid, I've changed the wording up here to reflect what it was supposed to be, because it was kind of confusing. It said in water, but we're really looking at acetic acid there. So the boiling point of water or of acetic acid is 117.9. And if we add that 0.12 to it, then we get 118. Oh, now that I think about it, there was a slide where there was some incorrect information. Let me go back and find that. I think it was this slide. I think here I had originally put solute instead of solvent. So you might go back and check your notes. This is when we were calculating glycerol in water. The X should be for solvent for this equation. All right. Anybody still need this? Okay. So we had briefly discussed this. I'm not going to go through the whole calculation, but it is on here if you want to reflect on it. Why do we add salt to boiling water when we're cooking? And we had said that really the molarity change is going to be pretty small, so probably that's not going to raise our boiling point a whole lot. So this is kind of a calculation of that. So if we wanted to raise the boiling point by 3 degrees, and then how much salt would we have to add to that? So a lot of times when you are doing these problems, I'm not going to ask you for the thing that's at the front of the equation. You're going to have to rearrange the equation. So what are we going to need to solve for in order to get to the amount of salt? Molality. Molality. So we're going to have to rearrange the equation to solve for that M. So you can either rearrange first and then plug in, or you can plug in and then rearrange. But we know that the temperature change we want is 3 degrees. We know that because we're doing salt, that sodium chloride, our Hoffe factor is going to be 2. And then this number would be given to you in the problem, or you would find it on a table. So 0.512 is just the KB for water. So when we rearrange that, we would find 2.93 moles per kilogram of water, and 1 liter of water should weigh about 1 kilogram. We do know that the density changes slightly, but we're going to just assume that it's pretty close. So if we know how many moles there are of the sodium chloride, how are we going to get to the mass?
Molar mass.
Molar mass. And so that's just going to be the 23 from the sodium, the 35.5 from the chlorine, which gives us the 58. And then that would give us 171 grams. So 171 grams, that's probably somewhere in the ballpark of half a cup of salt. So when you make spaghetti, you probably do not put half a cup of salt into the water to make it boil. You're not really going to raise the boiling temperature that much. Okay, so I said that freezing point depression and boiling point elevation, the equations are very similar. So you can see that it looks just the same. We just have to remember that because it's freezing point depression, the temperature is going to go down. So sometimes you'll see Kf is negative. Sometimes you'll see this equation with a negative in front of the IKFM. So it's written a couple of different ways. But like I said, just remember whatever number you come up with, your new freezing point should be lower than the original. So usually the temperature of something is pretty easy to measure, and we don't usually try and find that through a calculation, but we can use this to calculate a molar weight. And so this is going to be similar to what you would do in lab next week. So you are going to measure the temperature of a pure solvent, and then you're going to measure the temperature of the solution, the freezing temperature of each of those. And then you're going to use that change in temperature, the delta T, in order to determine the concentration and then the molar weight. All right, so let's say we have 5.0 grams, 0.1 grams of an unknown salt. So it's not sodium chloride. Anything that is ionic is sometimes called a salt. And it is dissolved in 100 milliliters of water. We're assuming that's also 100 grams of water. And we find the freezing point of this to be negative 2.05 degrees Celsius. So something that we have to know is what's the original freezing point of water? Well, I sort of assume you know this, do you?
Zero.
Zero, yes. So water normally would freeze at 0, but if it's got stuff dissolved, it's going to freeze a little bit less than this. Interesting consequence of this. Your freezer is not going to work very well if it's set to even -1 degree Celsius, because practically everything you put in the freezer is going to have something mixed in with the water. Like your ice cream has a ton of sugar and fats and flavors and things like that. So the freezer actually has to be set much, much lower than 0 degrees Celsius in order to work as a freezer. Anyway, okay, so we want to figure out, first of all, what's the concentration of the ions, and then figure out what's the molar weight. Now, what we would also need to know here is how many ions are formed. If it's a salt, we're going to make an assumption that this is 2 ions. The Van Hoff factor is 2. All right, so we've got our problem listed at the top. We've got our Kf listed at the top for us. And then we can start plugging things into our formula. So our total ionic concentration is going to be the Van Hoff factor times the molality. And so both of those are going to be incorporated into what we're solving for. So we don't have either the molality or I at the moment, but we do have the change in temperature and Kf, so we divide those. And why am I putting the change in temperature on top?
Because I don't know.
So think about when you rearrange an equation, you want to get the part that you're looking for by itself. So we're trying to get the M by itself, which means we need to divide both sides by K and by -1. So if I divide this part by negative Kf, then those will cancel out, but then I'm going to have to divide that side by negative Kf, okay? So I know that that is a skill from algebra, which you all had, but if we don't practice it, needs to be refreshed sometimes. Okay, so we figure this out to be 1.10 molal in ions. So that means that if we have MX2, M being whatever the metal is, because this is ionic, X being whatever the non-metal is, then the Van Hoff factor would be 3. And so we would say that 3M is equal to 1.10. Okay. And if that were the case, then you would just divide both sides by 3. And you would end up with this concentration. But this is a concentration, so we need to get, this should be mole per kilogram, not liter, sorry about that. Then we would need to go back to our original mass or volume there, 100, and get rid of the kilograms in order to get to the moles. All right, so let me fix this. This should be per kilogram. And this should be kilogram. There we go. All right. So is this a reasonable molar mass that we come up with? Actually, let's look at this second. So molar mass is grams per mole. So we take the grams that we know it is divided by the mole. So in lab, you're going to be given the grams of the solute. Probably it's just going to be written on the bottle. You're not going to measure it out. So you'll be given that, and then you'll divide by the number of moles that you have. Okay, so grams divided by moles, we get 136. Is that reasonable for a molar mass?
Yes.
Yes. What would be unreasonable for a molar mass?
Really low.
Okay, so how low is really low?
Like below.
Okay, so what about hydrogen?
The one, but you know, and I'm talking about it would have to be.
Right, so if we had a combination of hydrogen with anything other than hydrogen, it would probably be over 10. So if you ever get a decimal for a molar mass, if you had divided this upside down and you had 0.002 or something like that, then you should say, wait a minute, if hydrogen has a molar mass of 1, I can't have anything less than 1 for my molar mass. Most of the things that you do in lab are going to be probably somewhere between 50 and 500. If you're working with things like proteins, they can be much higher. Yeah, Sean? KF would always be provided. You don't need to memorize it, and you wouldn't have a way to figure it out other than doing a lot of experiments.
And MX2, that like, where did you get that from?
So that would be if you were doing this in the lab and your professor said, okay, I know that I have a basic formula of MX2. So that would have to be provided to you.
Okay.
What you could do, excuse me, if you didn't know the formula, you could say, okay, it's really common for I to be 2, 3, or 4. So I could figure out what would be the molar mass for each of these things. And then, yeah. But unless you knew how many ions it was breaking into, you wouldn't have that. All right. So we use freezing point depression in salting the roads in the winter. So when ice gets on the roads, when water gets on the roads, it's going to already be dissolving a lot of the salts and minerals and things that come from the asphalt and the tires and all kinds of things. So it's already going to have a freezing point that's below 32. But when you add additional salts like sodium chloride, potassium chloride, magnesium chloride, and calcium chloride, then it's going to lower even further. So if you were the person who was in charge of purchasing the salts to use on the road, and the place you're purchasing it from had these choices, what kinds of things would you think about when you were making your selection?
Van Hoff factor would be a big one.
So you would want to consider how many particles it's going to break into, right? So with the magnesium chloride and the calcium chloride per mole, you're going to get a bigger impact. Okay, so what are some other things?
Molar mass.
Let somebody else answer. So pick something else. Think like a business person. What's important to you? Money, yeah. Which do you think is probably the cheapest? Table salt is by far the cheapest. So I used to do a group exercise with this, and it's like a third of the cost of any of the others. Okay, so yeah, you could go with magnesium chloride or calcium chloride, but you're gonna pay more. Now, are they gonna sell it to you by mass, or are they gonna sell it to you by moles? Are they gonna say this is $10 per mole, or are they gonna say this is $10 per pound? They're gonna sell it to you by mass. So what do you think? Would I have more moles of particles for the calcium chloride at, say, 1,000 grams, or more moles of particles for the sodium chloride? So if I'm just looking at those two, for sodium chloride, sodium is about 23, calcium is about 40, right? So I get twice as many sodiums as I do chlorines for the same mass, but I'm also getting more chloride in there. And that's where the molar mass makes a difference. And so what we often find is that if we use the smaller salt, so sodium chloride as opposed to potassium chloride, you're going to get more of an impact. Magnesium chloride versus calcium chloride, you're going to get more of an impact. All right, now instead of thinking like a business person, think like a member of the community. This is salt that is going to be on the road in front of your house, might get in your yard, might be where your kids are playing. What else is important?
Low toxicity.
Definitely want to think low toxicity. Anything else?
Not being very,
Not being what?
like, being clean.
Okay, so you want it to be clean, yeah?
What's it say?
Safest, okay? And one of the things that goes into safety, aside from toxicity, is also going to be the impact on the structures. So it turns out that some of these minerals can actually start dissolving away concrete. So I know our driveway, which is a concrete driveway, we put the salt on it in the winter when it gets icy, and it's starting to break down because I think it's the magnesium that causes some of that concrete to dissolve and break away. So while it might be advantageous cost-wise for having a higher Van Hoff factor, it also might be destroying the roads, which in turn would make you pay more to fix them. So all of those things go into thinking about what you would want. Okay, so we had cost, the mass, the Van Hoff factor, and the solubility. Okay, so solubility, we talked about this one briefly before spring break, and this had to do with the thermodynamics of solubility. So we had one little section on that where we said sometimes it's endothermic to dissolve things and sometimes it's exothermic to dissolve things. So if it is exothermic to dissolve things, what's going to happen to the temperature?
Go up.
It's going to go up. Now, if you're thinking about melting ice on the roads, is that a good thing?
Yes.
Yeah. So sodium chloride is endothermic when it dissolves, but it's really, really small. So it's probably not going to make a whole lot of a difference. But both magnesium chloride and calcium chloride are exothermic. So in addition to helping to lower it by having the higher Van Hoff factor, they're also warming that ice, which helps it quite a bit. Which is why even though sodium chloride is by far cheaper, you might go ahead and use one of these other ones because it's going to be a quicker effect and help out a little bit more. All right, so just keeping in mind that it's not just the chemistry that's important, there's other stuff too. Okay, so now let's take a look at an example problem. We have a saturated solution of magnesium chloride. It is 5.7 molal, and we want to know what is the freezing point. All right, so remember.
And then water.
In water, yes. Yeah, if I don't specify, we'll say in water. And so remember our formula is delta T is equal to I M A F and KF is equal to 1.86. All right, and you are solving for this. And then the number that you get, you're going to subtract from the freezing point of water, which we said was 0. Okay, so take a second to try and do that. All right, so remember, once you have your delta T, your final freezing point is going to be equal to the, I'm gonna put a little 0 here to mean our original freezing point minus delta T. Okay, so how many of you think A, B, C, D? Excellent. All right. And that's where it's real important to remember it's freezing point depression, so it's going to go down. Okay, so our last colligative property is osmotic pressure. So for osmotic pressure, this is dealing with a very specific scenario. We have a semi-permeable membrane, which means some things can go through, in particular our solvent, and other things cannot, in particular our solute. So for example, we might have a semi-permeable membrane where water can pass through it, but salt can't, okay? So that semi-permeable membrane is going to allow the water to go from the pure side to the saltwater side. But it also allows the water on the saltwater side to go back. And what tends to happen is the whole system is trying to create both sides having the same concentration. It wants to mix together like entropy. We don't want to have separate systems. But we got this membrane that's keeping that from happening. So what happens is more water is going to go over to the saltwater side trying to dilute it, and less water is going to go back to the pure water side. Since the salt can't move, it just stays on the side where it is. All right, so the semi-permeable membrane, by definition, is a barrier that allows solvent molecules to pass through, but not the solute molecules. And often this is with water. Water is a very small molecule, which makes it easier to go from one side to another. But you could also imagine we might be talking about a gas, also very small molecules. And then the solute molecules, either because of their polarity or charge or because of their size, can't get through the membrane. So the first thing that happens is that the solvent can pass through in both directions, but more solvent is going to flow into the solution, which is the one that has the salt in it, than into the pure solvent. And that happens because it's trying to make both systems equal concentration. It's never going to be successful, but it's trying. All right, so we had a picture there where it was kind of like a fish tank, full to the brim on both sides. And then we had salt water on one side and pure water on the other. So if the pure water moves over to the other side faster than it comes back, what's going to happen?
Surface of the salt is going to go up.
Exactly. We're going to have overflow, right? On the solution side, it's going to get higher and higher. Okay, so let's say instead of in a fish tank, we have this in tubes so we don't spill stuff. Okay, so this is the same idea, but we're keeping the membrane down low and then allowing those to go up on either side. Okay, so we have both directions for the water, but mostly the water or the solvent is going to the solution side. And there's our semi-permeable membrane. And we have the net movement over to the solution side. Okay. Oops, I thought there was more to that picture. Okay. So the solution is going to become more dilute. There's the second picture. But it's also going to rise up. Now, when we have a column of air, liquid, fluid, whatever, it's going to push down. Gravity is going to cause it to push down. And the difference in the height between those two is going to create a pressure. That is the osmotic pressure. So remember way back when we talked about gas laws, this is kind of how we measure barometric pressure using a barometer. We look at how tall that column of mercury is. So here we're looking at how tall did the solution get? That's creating a pressure. So at some point, we're going to stop pushing water over, not so much because we've equaled out the concentrations, but because the pressure on the solution side is so great, it's forcing the water back in the other direction. So those two things become equal. So here, our net movement is towards the solution because there's no pressure difference. Here, they've equilibrated. And remember, with equilibrium, both things are going on at the same time. It hasn't stopped. It's just they're happening at the same rate. Okay, so the solution volume increases, which increases the pressure. And the solvent volume decreases, so decreasing the pressure on that side. And the pressure differential is our osmotic pressure, and that is going to affect the rate at which the solvent moves into the solution. So it's going to slow down the motion from solvent to solution. It's going to speed up from solution to solvent. So my thing, this is a scenario that is like so specific that it doesn't matter at all. It actually turns out this is an important scenario because it applies to cells. So every cell in every living organism has some kind of a membrane in it, and it is designed so that water can move in and out of that cell, but most particles can't move in and out of the cell easily on their own. So they need to have some sort of channel that they go through, which will allow the charged particles to go through, or they need a change in the cell that's going to develop it and bring it in, or sometimes particles just can't get in or out of the cell anyway. Okay? So those of you that are interested in healthcare fields, that osmotic pressure is going to be important. Calculating it is less important. Just being aware of what it is important. All right, so in order to equalize the pressure, you have to push down at with some pressure on there in order to equalize the volumes. So,
Or you put something harder, make it reverse.
right, and that's actually important too. So one other place that you might run into osmosis is if you are somebody who enjoys hiking or camping. You know that the water supplies aren't necessarily the cleanest water supplies out there. I mean, nature's going to do what nature's going to do, and we all got to poop. So you don't want to be drinking water that might be contaminated even by the natural stuff. So you want pure water. So if you want to get the stuff that's over here, what you can do is put the river or lake water on this side and then use your pump to force it in this direction. So because you're forcing it to go opposite of what it wants to do, this is called reverse osmosis. This is just briefly the calculation. I'm not going to stop on that. So you can get, if you're a hiker or camper, this is an older version. I'm sure they have newer versions now, but it's called a reverse osmotic pressure pump. And so, like I said, you would put in the stream water or whatever, and then pump out purer water because it has the membrane there that's going to stop any of the larger particles from going through. Okay, and then the top one there says it's used by cells to regulate the concentration of your electrolytes. So you may, in a biology class, hear about a sodium-potassium pump. That pump is kind of like this osmotic pressure pump. Okay, so I kind of skipped over this one because we started talking about reverse osmosis, but this is how it would apply to cells. Your blood obviously is not pure water. It's going to contain sodium, glucose, a variety of things. And so when you are in an isotonic scenario, most of the time, the concentration of all of these different particles outside your cells is pretty much the same as inside of your cell. And so the water flow is the same in both directions. But let's say you have a really high sodium diet, or you spend a week in the desert and don't drink enough, and you become dehydrated. So the concentration of the salts in the solution around your cells becomes higher because you have been having not enough water to compensate for those salts. And so more water flows out of your cells. And so that's called a hypertonic situation. You don't need to know that word. Where you are kind of deflating your cells. We actually use this in preserving foods. So if you think of the food called preserves, which is like a jam or a jelly, you just put a ton of sugar in there with that fruit juice, and it sucks the water out of any potential bacteria or mold or whatever, so that it dehydrates them. Now that's only going to work to a certain extent, so you can't leave it on your shelf indefinitely, but it certainly helps to preserve that for much longer than if you just had regular juice sitting in your house. And then the opposite can happen if you have too much water. So, you might think, oh, well, water is like the one chemical that can't possibly be bad for you, but you can drink too much water. And in part, this is what can happen. You can have so much water outside your cells that when you have the water going in, this can actually cause those cells to burst. And so you can see on the, what is that, right-hand side, one of the cells is kind of like a burst balloon. All right, so that's why osmosis is important, but we're not going to calculate. All right, we've been talking about ideal solutions. I keep saying that we're not really working with ideal solutions, but we are pretending we are. So in your book, it's going to talk about how you would really calculate the Van Hoff factor. In blue, dark blue, you see the real Van Hoff factors as calculated by experiment. And for most of the items that we would look at, the ionic ones, it's a little bit less than the number that we would actually calculate as a whole number. You are never going to have to worry about the ones that aren't ideal because, like I said, we're always going to pretend that it's ideal. So if we look at the ones that have 2 ions, they're pretty close. Sodium chloride and hydrochloric acid are pretty close. But as we move to ions that have a higher Van Hoff factor, then the difference can become quite large.
Or in how high charge.
Or what?
How high charge.
Or, yeah, it could be rather the charge of the ion as opposed to the number of ions. Definitely. Okay. So because this is going to be part of your lab next week, I want to go through another example. This is the one where we assumed the Van Hoff factor was 2. Yeah, let's go ahead and do this. Okay, so again, we have the formula, delta T equals IMKF, and we have 100 grams of water so that we can do molality. And the freezing point of the solution is -5 degrees Celsius. And again, we have 1.86 is our KF that we're using. And we want to determine the molecular weight of this salt. So we just plug in the numbers that we know. So 5 degrees Celsius is our change. We don't know what I is because it's an unknown salt. We do know 1.86. We don't know the concentration just yet. So there's 2 unknowns at this point. And so when we calculate this, we determine the molality of the particles is 2.69. So however many particles is in there, that's the molality of the particles. We multiply it by the 0.1 kilograms in order to get to moles, because remember, molality is moles per kilogram. So if I multiply by kilograms, those are going to cancel. And this 0.1 kilograms comes from the 100 grams of water. So I just switched that to kilograms, and that gives me 0.269 moles. But remember that this is moles of particles. I didn't write it on this line because the line was pretty long. And then to find molar mass, we would say, okay, what was the mass of our dissolved salt? And so that's the first thing mentioned, 10 grams. 10 grams divided by the number of moles gives us a molar mass, but this is the molar mass of, the average molar mass of the particles, okay?
So that looks like it.
So, oops. Since this is a salt, we would have to take into account that as well. So remember, we calculated IM, so to get to just M, we would divide by what I is. So if, say this were in lab, your lab instructor said I is 2, then you would divide, because moles is on the bottom. Then this whole thing gets multiplied by 2 and you would have 74. And then if you were savvy, you could say, salts that have 2 ions. It's probably a +1 and a -1. So +1s tend to be in this column. And then you could kind of figure out what the identity might be based on.
I think that's sodium chloride,
It is not sodium chloride because sodium chloride is 58.
potassium chloride maybe?
It's potassium chloride. Yeah. Okay. So that's one with ions. I'm going to very quickly show you something from the end of the chapter. Okay. So we aren't really going to dwell a whole lot on colloids, other than just to know what they are. What I want to look at is this picture. So what we have here is trying to distinguish between solutions, colloids, and suspensions. And so I usually think of colloids and suspensions as kind of being the same thing, but your book does differentiate between them. So the bottom is kind of our particle level representation. So really, what's the difference between all of them?
Close.
Yeah, the particle size. What's not clear in this picture is that for a solution, your particle size is going to be not how big your molecule is, but it's the molecule. Whereas in the colloid and in the colloidal, or in the suspension, you're going to have clusters of molecules.
Unless it's very low protein or something, then you can all have a half molecule.
Yeah, I suppose. I don't know what biochemists call, if they would say we have a solution of proteins. But if you think of like egg white, that is a clear aqueous solution that's got protein in it. Milk, whey proteins are in there. So, you could have that. So the first thing to remember is that when we're looking at the difference between this, both of these are clusters of molecules. It's just how big did that cluster get? So you could have this argument about, well, what is the dividing line between being a colloid and being a suspension? And I think your book says the particles are big enough that you can actually see the particles, like if you have a stick floating in a stream or something like that. I'm not worried about those things. Just if you hear the term colloid or suspension, that's not something that is going to be clear. It's not something that light passes through very easily. It's either going to be foggy or cloudy, or it's going to be opaque. So that's really the distinction between this and a solution. And the reason for that is that in a solution, there's enough water to completely surround each individual, either ion or molecule. The other thing, and we've got a picture here of milk, is your colloidal dispersion. So that's often the example we use. But we also have natural versions of these things. So when you have fog and you do like a spotlight or laser light up into the sky, then you can see where those lights are. But if you don't, then you can't see that. So you probably, if you have a garage door that automatically goes up and down, you push the button and it goes up and down, there's a laser that goes from one side to the other, so that if you're standing there and you're breaking the laser, if your cat's walking along there breaking the laser, it's going to say, nope, not going to go down. But if you, if there's nothing breaking that, then it will come down. But you can't see that laser because the air is a solution. But if it's a really foggy day, or if you dump over a bag of fertilizer and there's a dust cloud, then you would be able to see that laser light. Like in TV shows when they're trying to break into some place and they got all the laser lights going over everywhere. That's only possible if there's fog or cloud something in the air, some kind of suspension that is diffracting that light. All right. So you're going to have a pure chemical, probably boric acid, and you are going to find its melting point. And we know that the melting point or freezing point is where it becomes flat. So you're going to see what is the average here, or you can just put like a straight line back to the side here. And maybe this says this is 44.2 degrees Celsius. All right. Then you're going to do the mixture. And the mixture is going to have a slanted line. Now, this is a little bit dramatic. It's not going to be quite that slanted. But for that, I can't do the average of this because as the time goes on, it gets lower and lower and lower. So which of these numbers is going to be my actual melting point? So you're going to use the program on the Vernier graphical analysis, where you're going to do what's this straight line and what's that straight line. And this point here, which isn't even on your graph, that is going to be your melting point. So let's say this is 39.8 degrees Celsius. All right, so what can I determine from that formula based on this?
Molality.
Can I determine molality from two temperatures?
No mole flash. What the question is?
Just the change in temperature, that's all I got. Okay, change in temperature. So it went down by 44.2 minus 39.8. I'm gonna let one of you calculate that. Now, since both of these are organic, I is going to be 1. I will tell you that right now, that in your lab next week, I is 1. So your lab manual may even ignore I. KF is not going to be 1.86. We use that for all of our calculations today because we did water, but we've got a different solvent. So it's going to be something else. So I'm going to say it's 5.2. Yeah, 5.2 degrees Celsius per mole. All right. So now we can get to molality. 4.4. So we are going to have delta T, the T, divided by KF I, which is 1. And you said the temperature change was 4.4?
Yeah.
Okay, so 4.4 divided by 5.2. All right, and that is going to give us, since you have your calculator out, do you know what it is?
0.85.
0.85. Somebody else have it. 0.85 molal. And this is where it said it's really helpful to switch this M to what the units are, which is moles per kilogram. All right, and then just like we did in our other ones, you're going to have to use the mass of our solvent. And then that would give you moles. And then from the moles, use the mass of the solute to find the molar weight. But we're past our time here, so I'm not going to go through this.